Our final pair of reactions for aldehydes and ketones is what happens when we add either water or an alcohol to them. And while these sound like they might be two different reactions, we handle them together because they behave in exactly the same way. So we can start by looking at the addition of water. And usually this requires the presence of some sort of acid catalyst. But as a result, the water can add to the carbonyl. And you can see that we add an OH here and a hydrogen on the other oxygen. That gives us our total addition of water. And this product is known as a hydrate. Now, hydrates in many cases are unstable and will actually undergo the reverse reaction back to the carbonyl. But we mention this reaction because there are certain cases where the hydrate, for different reasons, ends up predominating. But the context of this reaction is more important when it comes to the addition of alcohols. And so we could add any alcohol. We'll use methanol here as an example. Again, we need an acid catalyst. And then there's two possible outcomes. One is that the alcohol adds once, forming a substance known as a hemiacetal or a hemiketal. In this case, because it came from a ketone, it's known as a hemiketal. If it had come from an aldehyde, we'd refer to it as a hemiacetal. And then sometimes this reaction will happen a second time. Now, what determines for this reaction whether it goes all the way to the ketal, stops halfway at the hemiketal, or decides it likes the starting material better and stays at the carbonyl? The answer is it depends on the starting material and it depends on the alcohol that we use. And without spending, the next 45 minutes describing different situations and how they would affect this reaction, we're just going to sort of leave it at that and say that, again, it depends very strongly on the specific reaction conditions. The one thing we will say, though, is in most cases, the carbonyl and the ketal or acetal. So if this reaction, again, we've said this, but let's write it out. And we'll use a different alcohol here, just to change this up. So if we start with an aldehyde, we can add the alcohol once. Or we can add it twice. And these are known as a hemiacetal and an acetal. Just like with the hemiketal and ketal, typically the one in the middle, the hemiacetal, is the least stable. And so most of these reactions either stay all the way to the left at the carbonyl, or they go all the way forward to the ketal or acetal. But there's one exception to that. And that one exception is actually very important. So there's a fairly important class of molecules, and all of these molecules contain both an aldehyde or ketone, as well as a number of alcohols. And here's one example. So here we have D-glucose. So we're talking about sugars. Now, if you've ever wondered why they're called carbohydrates, it turns out that in a carbohydrate, if you count up the chemical formula for any carbohydrate is some number of carbons with an equal number of water molecules. But sugars exist in two forms. We often refer to them as the open and closed forms. And this right here, D-glucose, as we've drawn it, we would call it the open form. But we have an aldehyde, and we actually have a number of different alcohols. And if one of those alcohols were able to react with our carbonyl, we could form a ring, and that ring would actually be a hemiacetal. Well, the preference for forming a ring is almost always going to be for forming either a 5 or 6-membered ring. In general, 5-membered rings form the fastest among different ring sizes, while 6-membered rings are the most stable. And so if the alcohol that I've highlighted in yellow is able to react with the aldehyde itself, then we get an equilibrium between the open form and this closed form. And this form is known as beta D-glucose, where the difference between the alpha and beta is dependent on which direction this alcohol points. But you can see here, we've now formed a hemiacetal. We have this carbon, which was the carbonyl, but it now has an OH group. The OH group was the carbonyl, and the other oxygen that's attached, this one here, is the oxygen that was this alcohol. And so this is a transformation that sugars can undergo, and that's what gets us back and forth between these open and closed forms.